Welcome to this explainer. I'm absolutely thrilled you're here. Look, if you're tuning in, you're a focused learner. You want structure, clarity, and you want to get straight to the heart of Cambridge mathematics. Today, we're doing a highly visual breakdown of statistics and probability. We aren't just memorizing formulas here, okay? We're taking raw data and turning it into serious exam-winning intelligence. Oh, and before we really get moving, make sure to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. All right, let's break this down step by step.
Okay, let's dive into this roadmap. We've got a fantastic four-part journey today. 1. Frequencies and unknown means. 2. Measuring spread and consistency. 3. Visualizing data correctly. And 4. Probability without replacement. Let's hit that first concept.
Section 1. Frequencies and unknown means.
You know, in statistics, the exam isn't going to just hand you everything on a silver platter. Sometimes you've got to play the role of a data detective. Look at this survey here. 200 people, favorite colors. We've got relative frequencies for blue, purple, and red. But yellow? Just a massive question mark. Now, remember, relative frequency is just a fancy way of saying the proportion of times an answer pops up, written as a decimal. The absolute golden rule you have to remember here. The sum of all relative frequencies in a full data set has to add up to exactly 1. It represents 100% of the people surveyed.
So, to crack this, we just subtract what we know from 1. We add up 0.12, 0.34, and 0.40. That's 0.86. Take that away from 1, and boom, the relative frequency for yellow is 0.14. But watch out. The command word in the question didn't ask for the relative frequency. It asked for the actual number of people. So we take that 0.14 and multiply it by our total survey size of 200 people. And there we go. Exactly 28 people chose yellow. Simple, right?
Now, what's really interesting about this next setup is how we handle two missing variables. We've got a table showing the number of movies watched by 60 people in a given month. But check out those frequencies down below. We're missing P and we're missing Q. The data tells us the total number of people is 60, and the mean, or the average, is 2.3. So how on earth do we solve for two unknowns? Well, we're going to need two equations. This is where we bring in simultaneous equations. Step 1. We know the sum of all frequencies is 60. If we add up the numbers we actually have, 14, 15, 7, 5, and 2, we get 43. So, P plus Q plus 43 equals 60. Subtract that 43 and there's our first equation. P plus Q equals 17. For step 2, we use that mean they gave us. The mean is the total movies divided by the total people, right? To get total movies, multiply the top row by the bottom row. 0 times P is 0, 1 times 14 is 14, 2 times 15 is 30, and you keep going, right up to 4 times Q. Add all those up, and you get 102 plus 4Q. Divide that whole thing by 60, and it has to equal our mean of 2.3. Multiply both sides by 60, and suddenly, 102 plus 4Q equals 138. Step 3 is where it all pays off. Subtract 102 from 138, you get 36. So 4Q equals 36, meaning Q is exactly 9. Substitute that 9 right back into our first equation, and P has to be 8. See? By setting it up systematically, the algebra literally does the heavy lifting for you.
Section 2. Measuring spread and consistency. Here's the thing about averages. They don't actually tell you if your data is tightly clustered or just completely wild. To figure that out, we need to ground ourselves in 4 crucial terms. The mode? That's just the most frequent value. The median is your exact middle value when everything is lined up in numerical order. The range measures your total span, highest minus lowest. And the interquartile range, or IQR, that one is absolutely crucial. It measures the spread of the middle 50% of your data, completely ignoring those weird extreme outliers on either end.
Let's actually put these to work on a dataset of 30 cars and the number of people inside them. What's our mode? Well, just scan for the highest frequency. 11 cars had exactly 2 people in them, so the mode is 2. The range. The most people in any car is 5, the least is 1. 5 minus 1 gives us a range of 4. Now the median requires just a bit more logic. We've got 30 cars. The middle of 30 falls right between the 15th and 16th value, so the 15.5th position. Let's count it out using the frequencies. The first 6 cars have 1 person. The next 11 cars have 2 people. 6 plus 11 is 17. Because our 15.5th spot lands squarely in that group, our median number of people is also exactly 2.
Okay, so how do we visually represent this? Say we want to show the cars carrying exactly 3 people on a pie chart. It's a quick 3-step process. First, find the frequency for 3 people, which is 7. Second, Turn that into a fraction over our total number of cars, so 7 over 30. Third, we know a pie chart is a full circle, right? 360 degrees. So we just multiply our fraction, 7 over 30, by 360. 360 divided by 30 is 12, and 7 times 12 gives us a perfect 84-degree slice of the pie.
And this brilliantly illustrates why measuring spread matters so much in the real world. Let's compare Class A and Class B on a math test. Who did better on average? Look at the median. Class A scored 64, beating Class B's 53. Easy win for Class A. But who was more consistent? For that, we look at the interquartile range. A lower IQR means the scores were tightly grouped together. Class A's IQR is 34, while Class B's is 41. So, Class A didn't just score higher, they were way more consistent across the board. A real game changer when analyzing performance. By the way, if you want to be part of a consistent group of top-performing students, remember to subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations.
Section 3. Visualizing data correctly. Turning numbers into a graph is powerful, but only if you know how to read the visual language. Look at this histogram showing travel times to school. Your brain immediately wants to look at the height of the bars, right? But notice how they're all different widths. In a normal bar chart, height equals frequency, but in a histogram, the area represents frequency. That vertical axis isn't frequency at all. It's frequency density. Huge difference.
So here's the million-dollar question. If the area is the frequency, how do we calculate it when we've only got frequency density on the y-axis and class width on the x-axis? It's literally just like finding the area of a rectangle, base times height. Or, in our case, frequency equals class width multiplied by frequency density.
Let's test this on the final block of data, students taking between 60 and 120 minutes. The width of this class is 60. Reading the graph carefully, the height or frequency density is 0.2. So step 2, multiply 0.2 by the width of 60. That tells us our unknown frequency, m, is exactly 12 students. Now for the final step. What fraction of the total students traveled for more than half an hour? We take the 30 to 60 minute group, which the table says is 18 students, and add our newly found 12. That's 30 students total. Divide that 30 by our grand total of 150 students surveyed, and 30 over 150 simplifies down beautifully to exactly 1/5.
Section 4. Probability without replacement.
This is where we shift from looking backward to predicting the future. Imagine a bag with 10 counters. 8 are blue, 2 are white. We pull one out, but, and this is absolutely vital, we do not replace it. Then we draw a second one. The first draw is super straightforward. 8 out of 10 chance for blue, 2 out of 10 for white. But let's follow that top branch. If we take a blue counter out first, what actually happens to the bag?
Seriously, think about the math here. Because we kept that first counter out, the entire universe of possibilities just shrink. The denominator permanently drops from 10 to 9 for the entire second draw. If we grabbed a blue one first, there are only 7 blue ones left, out of 9 total counters. The whole probability matrix fundamentally shifts the second you don't put that counter back.
Now let's calculate the real odds. To find the probability of a sequence, we multiply along the branches. Say we want 2 blue counters. We multiply 8 over 10 by 7 over 9. That gives us 56 over 90, which simplifies to 28 over 45. But what if we just want 1 blue and 1 white counter? Well, there are 2 ways to get there. Blue then white, or white then blue. Blue then white is 8 over 10 times 2 over 9, giving us 16 over 90. White then blue is 2 over 10 times 8 over 9, which is also 16 over 90. In probability, when we say or, we add them up. 16 over 90 plus 16 over 90 is 32 over 90. Simplify that down, and you've got exactly 16 over 45.
And there you have it. You see, by breaking down these frequency tables, analyzing data spread, cracking the code on histograms, and mastering those shifting denominators in tree diagrams, you're building an absolute powerhouse of an analytical toolkit. By mastering these underlying concepts, static numbers transform into a dynamic logic puzzle you already know how to solve. It's not just about getting the right answer. It's about understanding the very mechanics of the data itself.
I want to leave you with one final thought today. If a simple tree diagram can accurately map out and predict the outcomes of a few counters in a bag, how else are complex statistical models mapping the invisible probabilities of our daily lives? Everything from your insurance premiums to the weather app on your phone relies on the very math we just tackled. Thank you so much for joining me for this explainer.
Keep analyzing, keep pushing your grades up, and remember to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. I'll catch you in the next one.